a solid. And, for ice, it's what? C is 2100, 2100, right, joules per kilogram. Actually, per degree Celsius as well. Right? What would be the units of C? The units of C, the specific heat capacity would be an energy divided by mass divided by a change in temperature. So it's joules per kilogram per degree Celsius. But a delta T of 1 degree Celsius is also a delta T of 1 Kelvin. So you could also see that as joules per kilogram per Kelvin, right? So, but just for the purposes of the discussion here, suppose I have a mass of, I'll make it 10 kilograms. And I want this, solid number 1. And let me make the specific heat capacity of this. I'll just make it 5 joules per kilogram per degree Celsius. Right. And the initial temperature of this, I'll make it 20 degrees Celsius. Okay? What if I add to this object 1000 joules? All right. Now, I also have another solid number 2, same mass, 10 kilograms, same initial temperature of 20 degrees Celsius, but it's a different type of material, it's a different solid. So the specific heat C value, I'm gonna call it number C2, and I'll make it different from that. How about I make it, I'll make it 10 joules per, let me make this 5,000, okay, if that's okay. I'll make this, I'll make it 10. I'll make this 5,000. And then this was 10 joules per kilogram per degree Celsius, okay? And I add the same amount of thermal energy, 5,000 joules are added. Question, what will be the final temperature of this solid number 2, and what will be the final temperature of this solid number 1? So you can work on it, talk to someone. So notice that everything about these two objects is pretty much the same except for the specific heat. They have the same mass, they have the same initial temperature. I add the same amount of thermal energy to both of them. The question is which one will undergo the greater change in temperature? So let's find what the final temperature is so that we can figure out which one will undergo the greater change in temperature. So in fact, I'll write a delta T for this one. So go ahead and work on this. And I'll write a delta T for this one. And you can talk to someone if you like as you do this. I get to stretch. Am I blocking? The chair in the other room is better. Oh, maybe that one is better. Maybe this one is supposed to go there. Any answers? Yes,
Solid.
Kevin?
T final for 1 would be 120 degrees Celsius.
120?
Yes, sir. And then delta T would be 100 degrees Celsius.
Okay. And for the other one?
70 degrees Celsius and 50 degrees Celsius.
50?
50, yes, sir.
Agree? Everyone else? Good, thank you. So what do you notice? There's something to be noticed here. Same mass, same initial temperature, different type of material, therefore different specific heat capacity values. They both receive the same amount of energy. So, what do you notice? The one with the higher value of C is what?
You know, the lower temperature change.
So, which of the two has the higher value of C?
The number 2.
By how much did the temperature change?
50 degrees Celsius.
50. What about the other one?
100.
So, the one with the higher value of C is the one that, for the same amount of energy coming in, is the one that went up in temperature less or more? Less. So the higher the value of the specific heat for a given amount of energy coming in is going to go up in temperature less. The smaller the value of the specific heat, like this one, is smaller than that one, the greater is going to be the change in its temperature, you know, when you add the same amount of energy as you did for the other one. Yes? So if I take a styrofoam cup and I put coffee in it, and the coffee is too cold for me to drink, and I put it in a microwave oven, this sends energy to, you know, both of them, right? Which, when it's done, right, which of the two materials, the styrofoam cup or the coffee, has the higher value of specific heat? The one with the higher value of specific heat is the one that's gonna go up in temperature less. So you use styrofoam because then it's gonna go up in temperature less than the coffee, and you'll be able to grab it without getting burned. On the other hand, you might sip the coffee and you might burn, or, you know, put your finger in there, oh, it's hot. So just from that, I can tell that styrofoam material has a higher value of specific heat than the water that, you know, it's mostly water, right, for the coffee. Yes. What about a substance like sand? Like these days, it's very hot, right? You go there, you go to the beach, and you walk on the sand, bare feet, at, let's say, 1 o'clock, 2 o'clock in the afternoon, and you might have to step on someone you don't know, someone's towel. Or you run, you know, towards the water or something because you might burn your feet, right? But then again, same place, same day, you come back like late in the afternoon, and that sand is not going to be very hot. So what can you say about the specific heat capacity of sand at the beach? High or low?
It's low because it changes easily.
Low because it changes in temperature considerably in just a few hours. So sand is a material that has a relatively low specific heat. Or think of it this way, in the morning, it's cool, right? You step on it, not a problem, but then by noon, it's like, let me get out of here, so it goes up readily. If it goes up readily in temperature, it means that its specific heat capacity is low. Yes? So, I like to think, me personally, I like to think of specific heat, that C quantity over there, as a measure of the thermal inertia of the thing. So what do I mean by the thermal inertia? Well, let's talk about inertia. When you learned about inertia in Physics 185, or the equivalent of that course if you took it somewhere else, right? So what did you learn about inertia? You learned that Galileo Galilei is the person who discovered that the mass of an object is a measure of the inertia of the object. The mass is a measure of the inertia of the object. But what does that mean? What is inertia? So the inertia is, all objects have a tendency, as if they think, but they're not thinking necessarily, but they have a tendency to maintain their translational motion. So if an object is at rest, it's like it wants to stay at rest. But if the object is moving, it wants to keep on moving. It wants, as if it wants to keep on moving. And that behavior is called inertia. And when does an object have more inertia than another one? Galileo discovered the more mass it has, the greater that tendency, the greater that inertia. And the example that I like to cite when I teach Physics 185 is, think of an aircraft carrier. If the aircraft carrier, which has a lot of mass, if it is at rest in the ocean, maybe the pier, next to the pier, right? It's at rest. It's like it really wants to stay at rest. You want to make it move, you got to push it. And you got to push it hard, because it's like, it's like the aircraft carrier says, man, you got to push me really hard, because, you're not going to make me move. I really want to be at rest. But it also means that once that aircraft carrier is moving, right, in the ocean, with a lot of mass, a lot of inertia, it wants to keep on moving. You want to stop it, you got to come up with a big force in the opposite direction to make it stop. Or you want it to speed up, you got to come up with a big force to push it to make it speed up, because it's like it wants to maintain its translational motion. So objects have this tendency to maintain their translational motion. Said differently, objects resist changes in their translational motion. If they are at rest, they want to stay at rest. But if they're moving in a straight, if they're moving, they want to keep on moving in a straight line at a constant speed. Not speed up, not slow down. And a measure of that resistance to changes in motion. I'm not saying resistance to motion. I'm saying resistance to changes in motion, right? Which is the tendency of the object to maintain the motion, right? It's called the inertia, and a measure of that inertia is the mass of the object. The more mass, the more inertia, the harder it is to, change its translational motion. If it is at rest, it wants to stay at rest. If it's moving, it wants to keep on moving. And this is the reason why, for example, if we're driving our cars, right? So I'm driving my car, I'm going this way, and I have mass, the car has mass, and if someone cuts in front of me and I apply the brakes, the car stops, but my body wants to keep on going. This is not a decision that I make because I have a brain and I can think and reason, right? It's not, I mean, if I could decide that, I'll say, well, I'm just gonna stop myself too, right? So then I don't hit the thing. So I just keep on going straight, and that's why we need a seatbelt in case we hit something and then we don't keep on going and we don't crash into the windshield or the steering wheel or whatever. So we need a seatbelt, right? Although, if we were going and somebody comes in front and boom, we hit, right? The seatbelt can help us, stay in place, but then the head can, because we don't have a seatbelt for our heads. Imagine driving with, so we go, ooh, and then, you get whiplash, right? The same token, when you're sitting down, let's say, on your car, and maybe you're at an intersection waiting for the traffic light to turn from red to green, right? And then, when it turns to green and you start, moving the car, right? Your body's here, you're sitting on the car, but then what happens? The car goes forward, but your body wants to stay where it was. So of course you need the backseat to push you, right? So you go forward with the car. So at first what you feel is like, it's like you go backwards as the car goes forward. But it's not like you want to go backwards. It's not like I was here and just because the car goes forward, I want to go backwards. No, the car goes this way, you want to go back to where you were. So your body wants at rest, it wants to stay at rest. It has that tendency. And the more mass you have, the greater that tendency. So there is this thing called inertia, which was introduced by Galileo Galilei, and he discovered that the mass of the object is the measure of the inertia of the object. Later on in Physics 185, you learn about rotational motion, and you learn that there is this other parameter called the moment of inertia, rotational inertia, the capital letter I. When you write torques equals I alpha, that I, right, is an inertia associated with the rotational motion of an object. So the greater the moment of inertia of an object, the greater its tendency to maintain its rotational motion. So if it's spinning so fast, it's like it wants to keep on spinning at the same speed, angular speed. If it is at rest, it wants to stay at rest. But if it's spinning, it's like it wants to keep on spinning, right? So the greater the moment of inertia, right, the greater the inertia associated with rotational motion. The greater the moment of inertia, the more difficult it is to change the rotational motion, to make it spin faster, to make it spin more slowly. And that has to do with the distribution of the mass, right? mr squares, so it's like if you, anyway. So objects have a tendency to maintain their temperature. They resist not changes in motion, that would be the mass, or changes in rotational motion, that would be the moment of inertia. In this case, they resist changes in temperature. And a measure of that inertia associated with, the object wanting to maintain its temperature is the specific heat. Notice, the higher the value of the specific heat, it's like the higher the mass, the more difficult it is to change the translational motion. But in this case, the higher the value of the specific heat, the more difficult it is to change its temperature. And with this simple example here, right, everything was the same except for the value of the specific heat. And the solid, the substance with a higher value of specific heat, right, will resist changes in temperature more than the other object. So in this case, it'll just go up by 50 degrees Celsius, while this one is going to go up by 100 degrees Celsius. So I like to think of the specific heat of an object as a measure of the thermal inertia of the object. The mass of it is a measure of the translational inertia of it. And the moment of inertia, right, or the rotational inertia, is a measure of the rotational inertia of the object. So I just wanted to make that connection, that this inertia shows up again and again and again. Okay. We only have two simple equations here, two simple formulas, mc delta t, ml. And I want to consider situations or problems, solve problems where objects are mixed, substances are mixed. They have different initial temperatures, and we want to know what is the final equilibrium temperature that they reach. I don't care how long it takes it to reach that thermal equilibrium condition. I just want to know what will be the temperature when the things that I mix reach that same temperature. To say that they are all in thermal equilibrium is to say that they all have the same temperature. All right? So when we do that, when we solve problems like that, there are various ways of doing this. By the way, as I erase the board, I should maybe add this. If you look at a table with values of specific heat, you'll see that water has a relatively high value of specific heat. And that's a good thing. Water, a large percentage of our body weight and composition and so on is water. Right? And because water has a relatively high value of specific heat, it means that it is not easy to change the temperature of water, or to make it go up in temperature or go down. Yes? And that's kind of good. Right? Imagine if we have a lot of water in our bodies, and suppose the specific heat of water were really low. And we're in this room at 70 degrees Fahrenheit or so, and then we step outside when it's 100 degrees outside. It's like we get a lot of thermal energy, then our temperature would go up more readily. And that wouldn't be good for life, right? If you go up too much in temperature, you could die. But at the same token, if we, get in an airplane, flying somewhere where it's cold, and we're nice and, comfortable in the airplane, and we get outside, and it's like freezing cold. If water had a low value of specific heat, then our body temperature would drop considerably, readily, and again, our body temperature drops like below 92 degrees Fahrenheit, and it's like that's it. So it's a good thing that water has a relatively high value of specific heat. It resists, changes in temperature more than other substances, and that helps our bodies maintain a certain temperature, right? I mean, of course, if you stay out in the cold for a while, for a long time, eventually, you could die from it, right? If you just leave someone outside for a long time, because eventually it's gonna go down, but in temperature, but it's not gonna happen as readily as if water did not have a relatively high value specific heat. I mean, our bodies also have well, and I'll come back to that. When our body temperature begins to go up, our body says, we don't want that, that's not good for life. So we need to cool you down. So what happens is we sweat. And the idea of sweating is so that sweat evaporates from our skin. And evaporation is a cooling process. And I'll talk about that later. On the other hand, if our body temperature begins to go down, then the body says, that's bad. Your temperature needs to go up. And then you start shivering, right? The idea is to get, it's like, kinetic energy. It's like, okay, we need to raise the temperature of the thing. Anyway, I don't like being cold and I don't like being hot. I've been very hot and I've been very cold. Some of you know already, but I lived for many years in New York City. And in the winters, it can get very cold. And sometimes, I was going to school, waiting for the train, and it's like, to catch the subway to take me to school, or in the summers, just, so anyway, here you get it, a few days of the year, it's not so bad compared to, but anyway, some people really like those changes and not me. All right, so when mixing things, right, some things will be hotter than others, some things